Yeah, yeah, sure.
Yeah, Mr. Bain, um, yeah, I want to know why didn't we have the energy source selector in the final work? Okay, okay, I would love that. And then one more question, Mr. Bain. You see, the capacitors, the one used to filter out the energy and the voltage instabilities. We have one on the 100, sorry, on the VCC. That is okay. Okay.
very well in the evening. So please, I I will plead if you can throw some light on the I see no like brief in brief like because I was trying to follow back I was okay. Okay, sir. Okay, sir. So please, please, I want to know like, so where can I watch this video that you recorded? The less route distance, right? Okay, okay. Then please, okay, okay, sir. So then immediately after, okay. Thank you, sir. Okay.
Um, okay. So with the indicator LED you introduced, I want to know, is it in series with the whole board or in parallel? Because I'm thinking that if voltage passes through, we will have some voltage loss in there. Okay, thank you very much.
Sir, good morning. Please, my question is, yesterday when you were doing the description and the footprint, my question is, yesterday when you were doing the footprint and the description, you were copying from the net. Does it mean that when we are also doing ours, we should copy from the net or we should do? Okay. Okay.
I don't know of the same no.
Okay.
All right. Hello, please can you see the slides, and then can you also see me? Okay. The sequence is wow, that's interesting. My settings just unset itself. Okay. All right. Okay. Close. Okay. Google. All right. What is this? Oh. All right. This thing I don't know. Let's just use the normal thing and then go away. Okay. So let me share a window. No, let me share an entire screen. Okay. Okay. I don't know. I don't know what is happening, but my OBS software is actually misbehaving, and yeah. So my camera feed is not coming, but I have it for the recording though. Okay. So please, can you all see the presentation? Can you all see? Yeah. Fantastic. Let me just try one more thing. Monitor. Don't capture this. Let's see if it solves the problem. Preview, window. Wow. Just wow. Okay. All right. So sorry for the feedback thing. That is black. Okay. So yesterday I managed to talk about some of the components that we've used so far. I talked about capacitors, resistors, no, not resistors, diodes, and then but we talked about Joel. Adu, if you have a question, please you can go ahead. Okay. Uh, so we have used, if you check the circuit, you realize that we have used a lot of resistors, but I actually never talked about them. Now I know most of the senior members don't need it. However, for the sake of our youngsters, I'm going to do a little I'm going to touch on it a little bit. Then we can continue. Please, is that okay? Okay. Quickly check my camera video. Let's use Irene. Okay. All right. Can you see my video feed? Mm. Okay. Anyways, so was a little bit of concept. A little bit of concept. What do you know about resistors? Yes. Let's share something. What do you know about resistors? Those who already know something about resistors, just share with me. What do you know about resistors? What do you know? Mm-hmm. They oppose the flow of current. That is fantastic. What else? Any other? Any other? Okay, so you can parallel it with a cup and then use it as a filter. That is good. That is good. That's good. Any other? In what ways you used a resistor, or have you seen a resistor being used? Any of them? Just give it to me. Any of them? Yeah. Mm-hmm. Any other? Any other? Okay. So have you ever asked yourself why? Okay. Yes. Have you ever asked yourself why resistors are able to operate, why they're able to do what we just stated, the things that we just stated? Have you ever asked yourself why or how they do that? Okay. So by the end of this lesson, I'm just hoping you could get some basic understanding of all this. Okay. All right. So one thing that you have to note is that whenever if we have different materials, okay, so let's say copper, the material that we usually use in electronics, okay, so let's say copper, silver, aluminum, wood, and those and the likes, okay, when we take the same size, and I mean in terms of shape and other dimensions, when we take the same size, okay, and we apply voltage across it, what will happen is that we would measure different amount of current in them. Okay, that is a fundamental thing that you can actually test in the lab. Okay, you measure different currents in them. Okay, now if you pick something like the wood is actually not going to allow any current through it. Okay, in fact, even if you would be successful at doing that, maybe by the time you get a tiny amount of current to flow through it, you would have probably already destroyed the wood or bent it somewhere somehow. Okay, so materials like wood that do not allow a lot of that do not allow current to go through, we call them insulators. Okay, call them insulators. Now, if you take things like the copper, silver, gold, which we know are called conductors. If you take the same dimension, same length, same surface, same area, cross-sectional area, and you apply voltage across, you will still get them. Although they are conductors, you would still get them running different amount of current through them. Is that okay? Now, these materials, yes, because they are able to pass current, they are generally known called what? Conductors. This a lot of us also know from basic science. Okay. Now, every material, the reason this happens is that every material has a fundamental property that makes it resist the flow of current. In that case, resist electron motion. Is that okay? Now, this property is what we call resistivity. Okay. Now, take note. I'm talking about resistivity, not resistance. Okay. Resistivity, every material has this inherent or fundamental property that makes it resist the flow of current. Now, due to these differences, copper, aluminum, and the other element, they pass different amount of current at the same voltage due to these differences in this resistivity. Now, you usually see copper being used in electronics, okay, instead of probably, let's say, aluminum. This is because in terms of resistivity, copper's resistivity is very low. That is to say that copper is a good conductor of electricity than aluminum. Now, the trend here is that the higher your resistivity, the lower your conductivity. Is that okay? They are inversely proportional. Okay. So whenever we measure the opposition to the flow of current, when we consider a measure of the opposition to the flow of current, then in electronics, we are looking at a quantity called resistance. So two things, resistivity and resistance. These are two different things. Resistivity has to do is a fundamental property of a material. So it doesn't actually even depend on the size or the length or whatever I take. So far as it is copper, any piece of copper would have the same value. So if I take, let's say, a 1 gram of copper, the resistivity will be the same as 1,000 kilograms of copper. It doesn't change. Okay, it's fundamental. However, when you take resistance, resistance actually depends on the size of the material that you are using. Is that okay? So if I take a piece of, let's say, copper, two pieces of copper, one should be, let's say, 2 grams, and the other, let's say, 100 grams. Okay, definitely I can form, if I should create, let's say, a wire out of them, a wire with a cross-sectional area of, let's say, 1 millimeter squared or something, that will come with the 1 gram will come with a particular length. The 100 gram too will come with a particular length. Now, in this case, the longer the wire, the more resistance it will have. Is that okay? So the resistance of the material actually depends on the size, but resistivity does not. So irrespective of the size, the shape, resistivity will always stay constant. Resistivity always stay constant, and it is because of resistivity that we can measure resistance. So resistance is actually dependent on the resistivity of the material. Okay. Now, when you in normal circuits, we actually don't like the effect of resistance. Okay, so for instance, because of resistance, usually you have inefficiencies in energy transfer. Remember that I said that whenever the task of a circuit designer is to move energy from a source, which could be a battery, to a load, which could be something like a light bulb. Okay, and to do this, we use materials. Okay, the energy source itself could have some inherent resistance. The conducting wires that we are using to have their own have their own resistance. The bulb too, okay. And because of that, we are unable to transmit 100% of the energy from the source to the load. Okay, it always come up with losses due to the resistance of the material that we are using. Okay. However, in electronics, when we are able to control the amount of resistance needed, we can actually use it to advantage to do a lot of beautiful things in electronics. And engineers have actually created components out of this concept or this property of material, and that is what we call resistors. Okay, so yesterday when we were drawing out our circuit, we were using resistors in so many different forms, and always we were quoting names, values like 10K, 1K, 2K, and the likes. Okay, so resistors are circuit elements that have been created based on the resistance of material so that we can use them in a controlled way in our circuit. Okay, now all the components. Do I have any message? I'm not actually checking the feed. So if there is any message, please Just draw my attention. Okay, I'm not watching the feed. Okay. All right. Thank you. Okay. Now, all the components that we actually use in electronics can be grouped under two main categories. Okay, two main categories, and we are going to have a debate very soon. I actually anticipate it, but it's all good. It's all good. A lot of learning will be done from that. Okay, so we have what we call the passive components. Okay, I know probably has anybody heard of this before? What passive components are, and what do you know about them? Yes. What do you know about passive components? Or if you've heard about it before, what did you hear about it? Yes. Yeah, Sammy Watson, passive components. Yeah, you can go ahead. You can go ahead. Okay, it seems yes. Wusi, yes, you can go ahead. What have you heard about, or what do you know about passive components? Yes. Passive components. Wow, that's interesting. Okay. All right, well done. But after this, you will really get what they are used for. Okay. All right. We have Nathaniel. Nat, yes, you can go ahead.
Okay, so passive components do not require electricity.
They do not require electricity. Okay, I'll take that. I'll take it. We will refine it. Okay, we will refine it. We will refine it. Yes, Christine. Yes. Thanks, Nat. Thank you very much. Christine, yes. What?
Okay.
Uh huh.
Passive devices or components, they utilize the power or energy to the circuit.
Okay, so
They're like the conductors and the resistors.
okay, okay, that is good. That is good. Any other, any other, any other passive components. What do you know about passive components? I'm very happy to hear your take on that. Yes. Please, if you raise your hand, you can just I can see a lot of people have raised their hand. Just go ahead and answer. Okay, just go ahead. Uh, Elijah, yes. Okay. All right. Okay. So probably let's just continue. Okay, so it seems you all have an idea of what it is, and that is very good. Okay, that's very good. So let's see. So passive components, we can categorize components as passive or active. Is that okay? And please take note. These two labels are just one of the ways we could actually classify components. It's not like the absolute way of classifying components. Okay, we could actually also classify components according to their linearity or non-linearity. Okay, so this is just one of the things that we could do. Now, resistors actually happen to be passive components. Okay, so the question is, what are passive components? Okay, so one thing that you could always say about passive components that they have certain characteristics that or let me put it like this: components that are classified as passive have certain characteristics, and I'm going. The first of it is there is no power generation. Okay, they do not generate power. Is that okay? Now, they may dissipate like resistors. Okay, they may dissipate. And when we say that the component is dissipating power, it's like losing it, getting rid of it, or some kind of some sort. Okay. So a resistor in a circuit just basically dissipates the energy it's supposed to deal with. Is that okay? Now, if you take, there are some other components which are classified as passive. Now, they may not dissipate, but they may not only dissipate, but they may also store unused power in as a they may also store unused power. Okay, and a typical example would be capacitors and inductors. Yesterday we talked about capacitors. Is that okay? So this is one of the primary ways to identify passive component, the fact that they do not generate what power. Okay. Another thing is that they need no power sources to function. Okay. If I have to use a resistor, for instance, I don't have to provide some external power before the resistor can work. The same way, if I want to use a diode, a capacitor in my work in a circuit, I don't have to supply it with an external source before it can work. Is that okay? Now, what they usually do is their presence in the circuit influences the flow of power. Okay, so their duty is to influence our circuit, but they don't add energy to it. They don't require external energy to work. Now, here comes the debate. Is diode a passive component? Share your mind. Do you think a diode, if you yesterday we talked about diodes, we know that before a diode would work, it needs some to overcome some forward voltage and all that. So looking at whatever you know about diode, do you think diodes are passive components or they are not? Yes. Now, if you check on the internet, there is a very great divide on this, okay? And it's quite interesting. The the reasons people are given for to defend their choice is quite interesting. So let me know from you, what do you think? How will you classify a diode, active or passive? Do you think a diode is a passive component from what we just seen about passive components? Yes. Nathaniel, is your hand still up or it was for previous?
Hello.
Yeah.
Yeah, it's Joshua.
Joshua, yes.
Yeah, yeah. Okay. So based on the information you gave us previously, as in passive elements, one do not generate their own power,
Okay.
and two, they influence the flow of power. I would say diodes are passive elements, since
Okay.
one, they do not generate their own power, and then two, their presence could determine the amount of current that is being consumed by the entire circuit. So I would say diodes are passive elements based on the
Okay.
information.
Okay. Thank you very much. Thank you. Yeah. Christine, what do you also think?
I think they are active components.
Okay. Why?
Um, because yesterday, was it yesterday? Yes, when you were talking about, when you introduced about the Schottky diode,
Yeah.
and you said they also avoid overlays and poor surge protection and the reverse polarity. So it means they help in uh, in energy transportation. I can say that.
Okay. 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 That's good. Let's hear more views. Yeah. Kojo, what do you think?
It is passive.
You think it's passive? Any reason?
Because they influence the power
They influence the
to
power.
flow to flow in only one direction.
Okay. Okay. Yeah. Any other? Please come on. Come on. We are about 29
Um,
here. Yeah.
Hello, sir.
Yeah, Joshua.
Yeah, you've not described what active elements are, so
Okay.
I'm kind of confused if
Okay. All right. I
what
think
are
I
the
think you have a point there. I think you have a point there. So what I'm going to do is I'm quickly going to hide something in my PowerPoint, okay, so that we can have this debate later. Is that okay? Um, yeah,
okay?
I'm quickly going to hide something. So just give me a moment. Okay. Oh, come on. Okay. Okay. How do I even hide this? Hmm. Okay, I can do this. So, just a moment, please. I want us to really talk about this. In fact, I was actually surprised about the divide online. Lots and everybody. So the question is, are diodes passive or active? Big question. Yes, it's a big question that needs answers. So as I'll go over the passivity, okay? As I'm doing it, get your point right. So if you are for active, I want you to come up with a very strong reason. If you are for passive, I need you to come up with a very strong reason. Is that okay? Yeah. So yes, let the fun begin. Come on, don't waste my time. Just a moment. Hmm. Okay, good, 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 good. Okay, all right. So I'm going to present the whole thing again. So in case you didn't actually get the concept of, sorry, I have to take something away. All right. Okay, good. Okay, so I said that components could be classified into passive or two things, passive or what, active. Is that okay? Now, for the passive components, the one of their characteristic is just a moment. Okay, so for the passive component, wow, where did I get to? Yes, so for passive component, which a resistor is an example, one of their characteristic is that they don't generate power in circuits. Is that okay? They merely dissipate the power, or they may store unused power. Okay. And for the storage, we talked about capacitors and and inductors. Is that okay? Good. Then another is that for passive components do not need external power source to function. Is that okay? So, for instance, if I put a resistor in a circuit, I don't have to supply some power somewhere before the resistor can do its work of resisting the flow of electrons. Is that okay? And I also said that they merely influence the flow of power. Okay. So examples of passive components here we have capacitors, inductors. So the basic ones are capacitors, inductors, and resistors. Okay, but we also have transformers, thermistors, transducers, etc. Is that okay? Now, when we come to active components, one of their key characteristics is that they generate power and or, so that means they can do the two, requires some power to function. Okay, they can generate, or they can generate the power, or they may require uh, power to function. Now, take note of this very well. Okay, another characteristic is that when we change their input level, the input power level, we turn up modifying it outwards. Okay, we turn up modifying it outwards. So that means that not only does it require power to function, but the power that the nature or variation in that power also affects the way it works. Okay, that's another thing. So for active devices, the basic active component is a transistor. Okay, the most common and basic is the transistor. So now the question is, are diodes passive or active components? Discuss. Yeah, so let the fun begin. Do you think diode, from what you know about passive and active components now, do you think a diode is an active, or let me put it like this, will you classify a diode as an active or a passive component? Now, if you are following us on YouTube, please leave your comments below. Oh, actually, we don't have comment is disabled on this. Okay, fine. But you could probably chip in something on the platform. Yeah, so let's see. Do you think would you classify resistors as passive or active components?
Let's say
Okay,
resistance or
so yes, would you classify diodes as passive or active components? Somebody was, is it Ephraim? Yeah, Ephraim, please go ahead.
I'll classify hello.
Yes, sir, I'm listening.
I'll classify diodes as passive,
Okay, your point
as
being,
passive elements. My reason is that you see the diodes, they are unilateral elements. That is, they allow current to pass in only one direction. And we
okay.
also know that diodes sometimes serve as switches, and these switches they dissipate energy. And as we said, passive elements are the ones that dissipate energy, and active are the ones that generate it. So if they act as switches and they dissipate energy, and they're also unilateral elements which allow current to flow in one direction, then I personally will believe that their diodes are passive elements.
Okay, so just to clarify something, every component, one way or the other, dissipates energy. Is that okay? Just that resistors and most, yeah, resistors, for instance, are actually noted for dissipating energy. Okay, dissipating energy just means wasting energy in some way. Is that okay? And you realize that most components actually warm up in the course of operation, and that's also a means of energy dissipation. Is that okay? Yes, but there are components dedicated for energy dissipation, and those are the resistors you are talking about. So yes, understood. Understood. Any other take? Do you think diodes, or will you classify diodes as passive or active components?
Yeah, hello.
Yes, Joshua.
Yeah, so I previously said that diodes were active element and passive elements.
Okay.
I would like to change that.
You want to
So
change
now,
your stand?
yeah,
Okay.
yeah, yes, please. I would say diodes are active elements.
Okay. Why?
Because when we look at active elements like resistor and the capacitor and insulators, these elements
Wait, you
behave.
said when you look at active elements like what?
Sorry, when we look at passive elements
Okay.
like resistors and capacitors and then inductors. These elements behave depending on a certain characteristic they have, like an inherent characteristic, like maybe resistance and then inductance and capacitance. Okay. But then an element like diode doesn't have any sort of thing. And its operation depends on the power you supply. So if you power in a particular way, in a particular direction, it works, but if not, it doesn't work. I hope I'm making it clear.
Yes, I mean everybody is sharing their points, and I'm very happy to listen. So thank you,
So
thank you. Eh?
yeah, so I would say yeah.
They are active. All right. So we have 1-1. Okay. Somebody should do the tally for me. We have one vote for passive, one vote for active. Yes. Any other some of some of yes. Go ahead.
Hello, sir.
Yes. Lyrical. Go ahead.
Sir, please, for me, I don't know, but I think I'll take the passive one. In other sense, it can also be an active component. But
Why? Okay. So your points.
yes, for the diode, it doesn't require any external source to be able to function. What happens
Okay.
is that it just creates a unilateral path for current,
Mm-hmm.
meaning that it allows current to flow in one direction. But here the case, it can be used as an active device when it's used as a rectifier, because here you need an external source, let's say from the transformer, to be able to produce the DC in return.
But let me ask the question, right? Do you realize that the way we use diode as a rectifier is the same way we use diode anywhere, right?
Okay, sir.
So it's not like when we are using diode as a rectifier, it is connected in some special way. It is just the same way we connect diodes. Okay. So maybe just think about it a little. I want you to make your point, so that you are confident. I don't want that in the end you choose my answer for it, right? I want you to be able to decide for yourself. No, looking at this and that and that, I think because whatever stand I have taken is based on my understanding. You get my point? Exactly. All right. Nikat, yes. What do you think? I don't know if I got the name wrong.
Hello.
Yeah, hello. We are listening.
Yes, diode are the devices which do not generate power, but for proper functioning of the diode, we require minimum 0.3 to 0.7 volt tension. So I think it is active device.
An active. Okay, thank you very much. So what Nikat said is that diodes don't require external power. All right, so that is okay. However, there is this forward voltage drop that you always have to exceed before the diode can start operating. Okay, so because of that, he really thinks the diode is an active element. Good one. Yeah. So right now we have what 2-2, right? Is somebody doing the tally for me? Please, somebody do the tally for me. Any other takers? Any other takers? Do you think diodes are passive or active? Any other takers? Christine, would you like to revise your answer?
Okay. I think it can serve both according to how people are arguing.
Okay.
I think it can serve both depending on the type used or where used.
Okay.
But I think regarding the argument, to see where I stand, the moment can serve both as an active and a passive, depending on how used and the type.
Okay. All right. Thank you very much. 1 minute more. 1 minute more to close the post so that EC will come and declare the result. Yes. Do you think diodes are passive or active? Yes. Please. Let's rock. What do you think? All right. Could you? Yes. Could you?
I'm completely passive.
They are passive. Your reason being?
Because you already said that passive does not take electricity, and they also influence the flow of current. So diode also does not use electricity for anything, but it influences the flow of current to pass in only one direction.
Okay. By some yes. So we have three for passive.
I think diode is an active element.
Come again.
It's an active element.
It's an active element. Okay, your reason being?
Because it requires diode has an inbuilt voltage that emits, so which has to be overcome before it can serve the damage, allowing your natural flow of current.
Okay. All right. Thank you very much. Thank you.
I'm coming back.
Okay.
Yes, sir. Before I answer this question, I want to know what the diodes are talking about.
General diodes in general. I mean the basic PN junction diode.
Okay, so for the PN junction diodes, I think the passive component, because in this case, they allow current to move in one direction. So that will mean that they will act as a switch and as well split energy. And at this point in their working process, they don't require any external power source.
Okay, all right, fantastic. All right, one more vote, and then we continue what we are doing. Anyone? Koyo, you have already shared your views. I'm not
saying again, but I want to ask right from that. He said that the diodes have inbuilt voltage. So I'm asking the type of the current that they take.
Okay, right. I wasn't hear him. Yeah.
Yes, please. I heard. I think voltage. That means because let's say PN junction diode, for instance. So the P and then the junction between the P and N has, how do I say it? It has
I get your point. I don't even think it's okay. I don't think we see even understand the PN junction stuff. Okay, so you understand it. Oh, fantastic. Which level are you?
Computer educated.
Oh, okay. And you were taught you learned about PN junctions. Okay. So do you remember depletion zone?
Yes.
Do you remember anything called depletion zone?
Please don't really talk about that.
Whoa.
But I know the forward bias and reverse bias.
And they never talked about depletion zone?
Please no.
I see. Then it will actually be difficult to explain this to you. But don't worry, that's why we are here. How easy can I explain this to you? Okay, Pedro. Before a diode can work, okay, before the diode can work in the forward direction, before it can contact, okay, there is a certain voltage that needs to be exceeded Is that okay?
Yes.
Take it as you are standing at the back of a wall, and before you can see over the wall, you need to stand on a certain chair.
It's okay.
Do you get it? Exactly. So until you stand on that chair, you cannot see over the wall.
Yes.
Okay. So the same way, before a diode can conduct, it has to, let me put in quotes, stand on that chair. The voltage you are supplying, before any voltage could drive current through a diode, that voltage has to stand on that chair. Do you get what I'm trying to mean?
Yes.
Exactly. So it has to overcome it has to go beyond that threshold voltage before current to begin to move. That is what the voltage you was talking about. Okay. All right. Okay. Any last takers? Then I continue. Any last takers? I think we have less than 10 people voting. The rest, come on, talk to us. Okay. Okay. All right. So I'm going to tell you my stand. Okay. And if you think it's convincing enough, you can join me. Else, you can still read more about it and try to convince yourself and make a stand. Okay. All right. Let's take diode. Yes, the arguments, a lot of the activists, let me call them activists. Their main argument is about the fact that before a diode will work, okay, before a diode will begin conducting, yes, that barrier potential, which is the forward voltage, has to be exceeded. Okay, the forward voltage drop has to be exceeded, and until you exceed that, the diode is not going to work. That means that the diode is actually requiring power or energy before it works. That has been the main argument. Okay, all right. So point noted. Now, if we look at passivity, we say that for the devices or components that are noted as a one, they do not generate power; they merely dissipate or store them. Is that okay? So now let's look at diode. Does diode generate power? No. It rather consumes part of the power that you are supplied to do its work. Okay. The second point under passivity is that somebody should remind me. We said they do not require external voltage or external power in order to function. Okay. Whenever you are connecting the diode, you just drop it inside the circuit like that on the power line, and the moment the voltage across it exceeds its barrier potential, which is the forward voltage drop, current begins to conduct. And if you turn it upside down or to reverse it, it blocks. And of course, that is why we need it in the circuit anyway. Okay, so that is the diode's contribution to the circuit. The fact that once we use it in the circuit, it will allow current to pass in one direction. Good. Now, let's take something that we know to be an active device, transistor. Transistor has three terminals. Okay, collector, base, and I'm talking about BJTs. And even if you are talking about MOSFET, you have drain, source, and collector. You always connect your power between you connect the power on the VCC, the collector, and the emitter. Okay. No matter how much the voltage across the collector and emitter, if you don't apply energy to the base, the transistor will never switch on. But you see, that is not the same for a diode. If I connect that same voltage, I connect across the transistor's collector and emitter for a diode, the diode will begin conducting. Okay. But unlike diode, the transistor, you have to specifically and deliberately apply current to the gates. If it is a MOSFET, you have to apply voltage to the gate before it switches on. Okay. Now, previously, in a very long time ago, I used to be a diode as an active supporter. But right now, my stand is diodes are passive. Okay. Now, take note. This is my stand. If you go on and you see that, in fact, yes, and there are still people who are saying it can be active, it can be passive. Okay. But when I do my own analysis, I will classify diode as passive elements. All right, thank you very much. So you can read more about these things, okay, and try to convince yourself with something. Any questions after this point before we continue?
Yeah.
Okay.
Okay.
Yeah.
When you're making your point on the passive element, the first question you made was that consumes energy. And then, when you're listening and the properties of the passive element, what you said was they dissipate or store energy. I believe those two things are quite different. When they talk of dissipating, we are converting energy from one form to the other, or trying to make power with it. I don't know consuming that we are actually using it to do what we have to. Making sure that without using the energy to operate, our resistor is actually unlocking the energy by changing that energy, that energy into another form.
Okay, so if you okay, that's good.
Yeah, you did say that diode consumes energy. You say that it takes part of the energy and then sends it to the circuit. That's what you said.
Okay, thank you, Elsie. Is it Joshua, right?
Yes.
Yeah, so you see, that when I started my argument, what I said was the people who stand on the active, right? Their main argument is that diodes actually require energy, so like in your term, consume in order to start working. I made that clear. Okay, yeah. Now, that is convincing enough. But if you look at what we have actually defined for active, the thing is that they require another source of power to operate, not the same power they are operating, they are supposed to control. Do you get the point here?
Okay.
And diode is using parts of that. In fact, so the diode's usage of the power is parasitic in this sense. Because if assuming I just want to merely send current in one direction and at 9 volts, the diode ends up chopping some off, which is not actually ideal. Okay, and in an ideal diode, this is not supposed to even happen. Do you get the point here? Huh. So if you look at the active, the active thing, the thing is that the energy the thing is same thing that is using to. So that's why we tell me that an external source of energy. You get the point?
Frequency external source of energy.
So technically, that is how we put it. Just that when you talk, say external, somebody might think maybe yeah, taking another battery and maybe putting it. Okay, so I tried as much to take it away, right? But the thing is, the component is not part of the same energy, the power it is transmitting. Is that okay? Which in the case of diode, that's what it does.
And then
Okay.
talking,
Mm-hmm.
it was the total silver.
Okay.
And I was able to understand that when you look at passive elements,
Yeah.
I don't know if you get it. Look at passive elements, like the resistor, the capacitor, and the inductor. And these elements have some sort of inherent property, like the characteristic of themselves, like capacitance. The capacitor works the particle capacitance will float. The resistor also has the particle resistance of the series, and then the inductor and the capacitor likewise. But then the diode doesn't have any of these properties.
Are you sure that that property is supposed to make current flow in just one direction? That is the property.
So I mean, okay, I mean, quality. I don't know if I'm making
Yeah, I get what you are trying to say. Okay.
and then that.
I get what you're trying to say. Hello. I get what you're trying to say, but you see, that property you are trying to talk about, yes, resistors have resistance, capacitors have capacitance, inductors have inductors, right? That property you're talking about. You see, for diodes, that's what called the PN junction. It's actually its property too. Okay? It's actually the property. So the ability for a diode to allow current to flow in one direction is a property of a PN junction. I don't know if that is clear to you now. Okay.
I'll do more on that now.
Okay, yeah. But you see, PN junction's behavior is to allow current to flow in one direction. So that is their property too. Okay, it doesn't have, it's just like resistors have their resistance. The PN junction has a unilateral flow of what current. That is also their property. Okay, yeah. All right. So like I said, that is my stand. That is my reason. Okay, I'm not forcing it on anyone, but just make sure you find a stand and have a reason. Okay, that is by reading more, having a reason. Okay, it gives you some confidence to talk about it or to argue your point out. Okay, and I mean, in the end, it is not about whether a diode is passive or active. All that matters is knowing how to use a diode in your circuit and using it, right? But these things are just for intellectual gymming. You get the point? Yeah. So that's the reason I added this business. Okay, so let's continue. Unless anybody has some question that would need my answer. Whoa, OBS Studio disconnected. Wow. Okay, so if nothing, then let's continue. Thank you very much. Thank you very much. I think I've enjoyed the session. I've enjoyed it. Okay, so let's continue. Our passive and active elements, and we have successfully classified resistors as passive. Okay, let's continue with the notes on resistors. Now, resistance is, to take note, the component is called a resistor. Its quality or its characteristic or property is resistance. Is that okay? Now, resistance is measured in ohm. When we talk of an ohm, it's just an ohm is the resistance between 2 points, such that when 1 volt is applied across these 2 points, a current of 1 amp will move. That is how we define 1 ohm. Is that okay? However, you see, for instance, if I am working with little values like 300 ohm, 200 ohm, and that other, I can just say 200 ohm, 50 ohm, 36 ohm. But if you are working with things like 3,300 ohms or 1 million ohms, then mentioning this becomes inconvenient, right? So there is a way of nicely there is a way we nicely say these things, and we do so by attaching something called prefixes, to them. Is that okay? So with resistors, you will mostly hear of things like kilo, mega, giga. Okay, so for instance, 1,000 ohm, somebody, engineers or people, circuit designers will mostly like to call it 1 kilo or 1K for short. Is that okay? So we have a K for kilo, capital M for mega, capital G for giga. Okay. Then we can also have lower values. In fact, when you are working with shunt resistors, you can have values like 0.01 ohms. Okay. So things like that, we can use a milli prefix on them to make them look nicer. Okay, so if we have something like 3,300 ohms, we could call it 3.3 kilo ohm or 3.3 K. Is that right? So when we start the PCB, you hear me saying, calling out resistors according to their value and a prefix. Okay, so something like 10K, 2K, 1K. Okay, so usually the rule of thumb is any value between 0 to 1,000, just call it out in full, because they don't require any prefix, right? So maybe 860 ohm, 620 ohm, 470 ohm, just that, right? But anything above, then you start introducing the appropriate what? Prefix. Okay, so 1 million ohm will become 1 mega ohm or 1 meg for short. Then if you have something like 0.01 ohm, that would become, I think, 10 milli ohm. Okay, and that makes everything looks nicer and easy to mention. Is that okay? Now, there are different types of resistors out there, and based on the type of resistor and even its form factor, the way their values are coded or printed on them may differ. Now, common true hole components, and I'll talk about true hole components probably today or tomorrow. Resistors have color codes. Okay, so those of you who have used resistors before can see that they come in bands, and these bands, colors of bands, actually, if you know how to decode them, that tells you the value of the resistance. Okay, some resistors can also have numeric coding. Okay, so on some resistors you see something like 402. So 402 would be 40 times 10 raised to the power 2, okay, which is like 4K. Is that okay? So if you know how to read them, you can always find out. But I'm not going to go into that details. I just drew your attention so that you can learn more about that. So if you are interested, please get any material on resistor color codes and learn more. Okay. Now, when we started, I asked about what do you know what do you know about resistors, what they are used for? And a lot of you said something that was very interesting. Okay, that's good. So generally, remember from the beginning, I said that materials have an inherent ability to resist the flow of current, right? So generally, generally, uh, generally what do we call it, I was looking at something, sorry. Generally, we need resistors in the circuit because we want, you see, electronics about controlling the flow of current, right? It's about control. Electronics is always about control. So one of the ways we control current is also by determining how much of it should move and where. Is that okay? So having a means to tell how much of current should move, that is what resistors are used for. Okay, so we use them to reduce the amount of resistance of current that's supposed to flow. Now take note, I don't know any situation where resistors are used to increase. Okay, their primary action is to reduce. Okay, to oppose the flow. Okay, now with this in mind, because of this property, resistors can be used to divide current or divide voltage, and we shall look at that very soon. Okay, resistors can be used for these two things, either dividing current or dividing voltage. Now, commonly when we use it to divide voltage, we call it a voltage divider. And I know most of you have heard of it. You probably heard of voltage divider or potential divider. They actually represent the same thing. Is that okay? Now, anytime we connect resistors in series, and by series arrangement, I mean the leg of one to the leg of another in that order, okay, in a linear form, something like that, then we have a series arrangement. Anytime we have that kind of series arrangement, what happens is that any voltage that we apply across the two resistors will be divided according to the ratio of their resistances. Okay, so that is what makes it possible to use resistors as voltage dividers. Then we can also use resistors as current dividers, okay? But in this case, we have to connect them in parallel to each other. So if I have two resistors, I tie two legs together and the other legs together, okay? Then I've created what we call a parallel circuit, okay? In that case, the same voltage will drop across the two, but then what do we call it? The current that will flow through them would vary, okay, according to, once again, their resistance, different current. So take it as this: if you have a bigger pipe and a smaller pipe, and you've connected all of them together at the same entrance or at the same point in a water flow, okay, you realize that the bigger pipe is going to allow more current to flow through it, okay, but the smaller pipe will allow little amount of current to flow through it. Let me water. Will allow a little amount of current to flow through it, okay? So that's the same concept when it comes to paralleling two resistors. You divide the current among them. So in terms of potential division, okay, this is how it looks like. So if I have, let's say, a V in, and I have two resistors, R1, R2, and I apply the voltage at this junction called V out would be governed by this particular equation, okay? R2, which is the resistor that at the bottom, divided by the sum of resistors. Now, if you check this well, you realize that the only thing we are doing here is ratio. Is that okay? So this gives us a ratio of this R2, which is the determining factor for this voltage. This ratio over the total resistance in the circuit times the total supply, the total voltage, the supply voltage. That is how you get the value of what? R out. Okay, so as an example, let's say our V in is 12 volts and R1 is 10K, R2 is also 10K. Then the ratio is going to be 10K divided by 10 plus 10, so 10K divided by 20K, which will give us half. Okay, Now, V in is 12, so half of a 12 would give us 6. That means you are going to get a voltage of 6 at this point, okay? And you realize that in this case, the 12 volt has been divided equally because the resistances are what? Equal. Is that okay? Now, the way you create potential dividers with two resistors, it could be this, it could be that, it could be this. In each of this scenario, we have potential division among across. We have potential division. Sorry. All right. So, any questions on this before I continue? Any questions on this? I think I heard the chat text. We are seeing your face. So, are you trying to say you are not seeing my face or you are seeing my face? Please, do you see the PowerPoint? Hello, are you guys seeing the
Yeah,
PowerPoint?
hello. I'm not seeing the PowerPoint.
Oh, really? But I can see it here.
I don't know of others.
Yeah, I can see it.
Yes, I can actually also see it
Please, I can
here.
see it.
I can also see it.
Okay, so thank you very much. So the one getting that problem, please check it. Okay, thank you. All right. So any questions on this before we continue? The voltage division. I mean, I plan to do some weekend training, some weekend tutorials to be open for anyone who wants to join. It is mostly going to be on Saturdays. Maybe I'll start in January. Okay, where I would actually go into details some of these concepts that we are looking here. Okay, for instance, if I take capacitance, I'm going to talk about them a complete tutorial on capacitors, both theoretical and practical. Okay, so this one is just to give you an idea, and especially the beginners, supposed to give you a clear idea of what we are trying to do here. So if you have any questions, please. Okay, so if no question, then let's continue. If no question, let's continue. Okay. All right. Okay. So when we connect resistors in parallel, usually what happens is that I even just said it, the total current is splitted, okay, between the resistors, and the splitting is according to their resistances. Both voltage division and current splitting depend strongly on the resistances, okay, the value of the resistances, okay. So this is a typically when you are splitting, this is what will happen, okay. So this is a parallel connection of two resistors. If you look at the previous one, see, this is what we call a series arrangement. So one here, one there, like that. This is called series. And in series, one of the characteristics of a series arrangement is that the same current is going to flow through them. Okay, the current that will get into R1 is the same that will get into R2. Is that okay? No matter what, no matter the size of R1, whatever flows into it, that's the same thing that will flow into R2. Okay, so in series arrangement, resistance is actually split, voltage is actually splitted, but current remains constant. Okay. And then when it comes to for parallel arrangement, if you can see that over here we have the same voltage across the two. Is that okay? So for parallel arrangement, the voltage across them will stay constant. However, when the current gets in here, according to their resistances, different amount of current will flow. And the way you calculate for that is by using this particular relations here. Okay, so if I is the total current coming through, then again you see that we have a ratio factor over here. Okay, so for R2 we have R2 over R1 plus R2, which is R2 over the total, and here for R1 we have R1 over the total. So it's all about ratio and proportion, both voltage division and current division. Okay, yeah. So any questions? Any questions? Any questions? Any questions? I thought somebody entered. Okay. Okay. So let's continue. Okay, let's continue. Now, resistors and any other resistive components. Okay, by saying other resistive component, I mean components that behave like a resistor. That means they dissipate energy just like resistors, and there is a linear relation between their voltage and current consumption. Okay, something like an incandescent bulb, not the one powered by AC, but the one that we power by DC. Okay, all these are resistive elements, and any resistive element obeys something called the Ohm's law. Okay, obeys Ohm's law. Who remembers the statement of Ohm's law? Does anyone remember the statement of Ohm's law? How do we state it? How do we state Ohm's law? Yeah, Kojo, yes, if you remember, let's hear from you.
The Ohm's law, the Ohm's law states that the current across the resistor is equal to the current flowing through the circuit.
Can you take it again?
The Ohm's law states that the current across the resistor is equal to the current flowing through the circuit.
Okay, well, we will have to correct that. Okay, I don't know if it is just an omission, but we have to correct that. Yeah, Hassan. Yes, Hassan.
It says that in metallic conductor, the,
Is it Nat is speaking, right? Nat, are you the one speaking?
It seems someone is speaking already. When is that?
Yes. Okay, Hassan. Yes, you raised up your hand.
yeah, okay. So I said it states that in a conducting material or in a metallic conductor,
I
the
I really
current
can't I really can't hear you well. Yeah, can you take it again? Okay, Nat, try it. Let's see. You get back to Hassan.
Okay, so Ohm's law states that at a constant temperature, the current passing through a conductor is directly proportional to the potential difference across its end.
Fantastic. That is so cool. Any other? I mean, it's a statement. You could also put it in any other way. Yeah. Hassan wanted to try. I don't know if he still wants to. Okay. Abdul Basit. Yeah. Please give it a
Yes,
try.
yes. Okay, this law is saying voltage is equal to the current times the resistance.
Okay. That's fantastic. That's fantastic. Okay. So that is the statement. But now the question is, how do you understand it? Can somebody use any practical means maybe to explain it? I mean, it's easy to keep the statement in your head, but practically, do you understand it? If you have a circuit, do you know when to apply Ohm's law? Yes. Yeah, Hassan. Yeah, Hassan, you can speak.
okay, can you hear me clearly now?
Come again.
Okay, can you hear me clearly?
Yes, I can hear you. I can hear you.
Okay, so let's take for instance we have a circuit whereby we have an LED. So we want to
Mm-hmm.
light up an LED,
Yeah.
and we also have a battery. So let's say for
Mm-hmm.
instance 3 volt battery,
Mm-hmm.
and we intend to light up an LED, and we all know that definitely it is not advisable to like power the LED directly on a battery. So because those LED their currents are usually like very low. So it is preferable for us to like use a resistor. So and using a resistor in this case, okay, probably let me not take it to that aspect. I think I'm
Okay.
going too far. Okay, so like in a let's assume we have a lamp and we have a resistor in the circuit and we have a constant battery. So if we should vary the okay, let's say if the resistor is constant, I
Mm-hmm.
don't know. Okay,
Yeah, feel
I'm
free.
just
Feel free. For me, I'm
okay.
following. I'm following. Uh-huh.
Okay. Okay, so let's say we have a circuit whereby we have a lamp and we have a resistor, and also we have a battery. And if we should vary the value of the resistor, let's say probably we should increase the resistor, it will definitely what reduce the flow of current. And
Mm-hmm.
also if we should fixed, if the resistor is resistance is fixed, resistance of the resistor is fixed, and probably we increase the voltage of that particular battery, so the current will also increase. That is directly proportional. So increase in voltage will bring about increase in the current if we should have a constant resistance. So that is what resistors
Okay, okay.
basically.
That is great. That is great. Any how do you understand the concept of Ohm's law? Yes. Any other?
Hello, sir.
Yeah, Joel. Yeah.
Hello, sir.
Yeah.
Please, my my contribution is that when we take it practically, it's like a pipe
Mm-hmm.
which water is flowing through.
Okay.
Like when there is no obstacle in the pipe, like maybe some dirt or anything.
Mm-hmm.
When there is no obstacle in it, the amount of power that the water that is flowing from the source should be the same as the amount of water that is coming out from the pipe.
Mm-hmm.
So, in that case, the obstacle here that we are talking about will be the resistance.
The
Uh-huh.
resistance. Okay.
Uh-huh. So, and the source will be the voltage. So, when there is no obstacle, the water that is coming out from the source of the
Mm-hmm.
water will be the same as the water that's flowing out from the pipe. Like that's
Okay.
my practical
Okay.
idea.
Okay. Thank you very much. Yeah.
Hello, sir.
Any other? Yeah, Ephraim.
Hello.
Yeah, Ephraim.
Yeah, it's like let's say using a fan regulator
Okay.
to maybe to control the fan speed. So you can regulate the speed of fans in our houses. So by controlling the resistance through the regulator, the current flowing through the fan is also managed. So like this is like an example of Ohm's law to me.
Okay, 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 fantastic. Yeah, so in fact, I'm enjoying this. I didn't anticipate this, but I think I'm loving this. Okay, yeah. Any other take? Nat, yes, Nat. Let's hear from you. Oh, you already, Christine. Okay, Nat, take it. Okay, Nat is out. I think. Christine, yeah. How do you
No,
understand Ohm's law? Yeah.
I wanted to say the same point as the one who was explaining about the water in the pipe.
Oh,
The more
okay.
the flow of water, the more the pressure,
Okay.
and the
Okay.
bigger the pipe.
That's great. Any other? Any other? Adam. Adam. Yes.
Yeah, I also want to add
Okay.
to say that at constant pressure, the current
Mm-hmm.
flows remains the same.
At come again.
Constant pressure.
So here pressure
I
will
mean,
be
at
the
constant
voltage, right?
voltage,
Uh-huh.
yes. And then the push out, the current
Mm-hmm.
flowing remains the same.
Okay. 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 Wow. That's cool. That's cool. Any other before uh, I chip in? I've really enjoyed the submissions. Yeah. Any other? How do you understand Ohm's law? Yeah, we usually, yeah, Ohm's the potential difference across blah 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 blah. But how do you understand it? Because when you understand these laws, okay, knowing them is not the same as understanding them. Okay, you could be familiar with Ohm's law, V equals to IR, but what does it really mean? Okay, what does it really mean? Okay, let me see. Let me see if I could do some demonstration with circuits. If I can do this simulation, circuits simulator, online circuit simulator. I haven't used this, but let's give it a shot. We're going to see if I could use it to explain something. Okay. Yeah. So still, I'm asking for your input. How do you, okay, so somebody is saying that, is it advisable to use resistors as voltage regulator? Let me, I think yesterday I talked about that. Is it advisable to use resistor as a voltage regulator? No. And I'll explain why. Okay, you don't use it now. Depending on in some applications, yes, you may be able to, but generally not, because you don't get the ability that you want. Okay, let's hope this thing works, and I can use it to explain some things. Else I may have to resort to paper. I know KeyCard has a simulator, but it's not something I've used. So, oh, come on. Okay, probably I just have to resort to. Okay, okay. Let me just do something real quick. I want to do something real quick. Show you, explain this whole thing, Ohm's law, and then at my tablets. Yeah, so if you still have a contribution, please, we will be glad to listen. Ohm's law, how do you understand it? Yes, you can quote it, you can state it, but what I'm actually asking a question, we are asking right now, your understanding of Ohm's law. Okay, how do you understand Ohm's law? I'm trying to do some setup. Okay, yeah, I can write now. Right, that, okay. So this is what I'm going to do. I'm going to switch screen. Where is my monitor? Primary. Yeah, this taking from YouTube. Sorry for the disturbance in the feed. I just want to explain something real quick. And then let me move this here. Probably stop sharing. Okay, and now share this screen. Okay, alright, fantastic. Okay, so let me open Paint. Let's just use keypad. I wanted to do simulation, but none of my simulators are installed. Okay. So, Ohm's law, right? How do you understand it? I'm going to try and explain something. Now, all of you did well. You gave what you gave was actually right. I just want to add up a little to it. Okay, I want to add a little to it. I can actually use this. Let's go, please. I just want to add just something tiny to it. But the moment you get this kind of understanding, you really appreciate it when you are doing it. Now, can you all see the Paint app? Can you all see the Paint app?
Yes, sir.
Okay, good. So my first question, somebody explained with LEDs and resistors, okay, and that actually drew my attention to something. Let's say I have a voltage source which is 2 volts, okay, and I want to power up an LED, let's say a red LED, okay. Now, red LEDs are actually, they actually take about 2 volts, okay. and ideally you should run a current of about 20 milliamps through them. Is that okay? I think this would have been very nice using. Okay. Now, if I have this, my question is, do I still need a resistor in this? Do I still need to connect it? So let's say, can I just hook this up like that, then to ground, right? Without a resistor. Can I do this? Come on, share your view. Can I do this?
Hello.
So I have 2 volts power source, right? It could be a battery that is 2 volt, and I want to power an LED. This LED is red, and red LEDs usually take 2 volts, right? So my question is, do I have to connect a resistor in this circuit? All right, lyrical, yes. Let's hear from you.
Thank you very much, sir. Sir, with this type of circuit, I think connecting a resistor will not be necessary
Why?
because once a resistor is connected, there will be a voltage drop across the resistor. Hello, sir.
Yes,
Hello.
I'm listening. I'm trying to adjust the feed for the online people. Yeah, continue. Yes. Are you done? Are you done?
Sir,
Yeah.
I think that before you consider connecting a resistor to the LED, you
Mhm.
must also check
Because
the current rating
once
of the voltage source. So
The
if you
current
check
rating of the voltage source. Okay, so let me add this. You see, let's assume that this voltage source can produce an infinite amount of current. Is that okay for you? So
yes, sir.
the voltage source is capable of driving any amount of current that you want.
Okay.
Do I need a resistor?
okay, sir.
Mm-hmm. Yeah, Nikat, you can chip in. Yes,
Because
I'm listening.
considering
Uh-huh.
the voltage,
Lyrical, continue. I'm not hearing you.
Hello.
Yeah, Nikat, yes.
Hello.
Yeah, Nikat, go on.
I think I
sir,
think there is no need
sir,
to any
sir,
register.
I was saying that
Okay, so Nikat said there is
Lyrical,
no.
somebody from the line.
Hello, please, let's be aware when somebody is speaking, okay? So Nikat said that there is no need to add a resistor. That is good. Yeah, Lyrical, what do you also say? Yeah, or any other. Do you think we need a resistor or not?
hello, sir.
Yes, sir.
Sir, please can you hear me?
Yes, I can hear you. I can hear you.
I was saying that we don't need a resistor because we create a voltage drop which might not be able to power our LED here.
Okay, 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 okay. Good. Elijah, yes, Elijah, what's your take on this?
Hello, sir.
Yes, sir.
Please, I think we need a resistor because you have to know the current coming from the source. So that if the current coming from the source exceeds the specification of the LED, then you use a
Mm-hmm.
resistor to limit it a bit,
Okay.
so that at least you can be able to power the LED.
Thank you very much. You just made a point on the reason I wanted to do this. Okay. Thank you very much. You see, let's go back to Ohm's law. Can somebody repeat the statement for me again?
Yeah,
Mm-hmm.
can you hear me?
Yeah.
So it usually says that voltage is nearly proportional to current when the resistor is constant.
Okay. So mathematically, we express Ohm's law as what? The voltage drop, the current, right? And the resistance, right? Okay, so when we take any conductor or any element, we can assume this, unless it is a variable, and we can assume this to be what? Constant, okay? And this is actually a property of the material itself. Do you understand that? You see, one mistake, or I won't say mistake, one misunderstanding I see a lot of people get about power sources is that most people think, okay, uh, currents would be like the same way I can put voltage across something. Current can force its way through something. No. Now, please take this from me. This power source here, this 2 volt, even if it could generate an infinite amount of current, that current will only come when it is requested. Take note of this. Current is a reaction. Okay, current only comes or moves when there is voltage. Okay, now if that is the situation, look at this. If this material is rated 2 volts, what it means is that if I connect these 2 volts across this, it is by default going to request for the current it needs and not more than that. Why? Because now, unfortunately, this is an LED. It is a linear device, right? So let me just use something that is a linear, an ohmic device. So let's say instead of LED, I'm using a lamp. Okay, I'm using some DC lamp. Come on. Okay, so instead of an LED, just to make my point, okay, just to make my point. So instead of an LED, let me put a lamp here. Wait, wow. Okay, how do I change this? Okay, yep. So instead of an LED, let me put a lamp here, right? You see, if this lamp is rated 2 volts and let's say 20 milliamps, if I connect 2 volts power source, which even has an infinite amount of current, it is just the 20 milliamps that will flow. Take note of that. Okay. Current doesn't force itself through a circuit. Current only moves at the command of voltage. Please, are you following? Current will only move at the command of what? Voltage. Good. Now, I have to. Okay, good. Okay, so look at this. In a situation where, let's say now I have this voltage is 3. Now I change this to 3 volts, right? And this lamp is still 2 volts. In this case, it is like I am putting too much pressure on the lamp. And this pressure is it because this pressure is so much, it is going to also force so much current to go through. So here we are going to get excess current flowing because of the excess voltage. Okay, but so far as we match voltages, we don't have to worry about current. So when I'm actually designing things, I don't actually even worry about current, because the point is that if you set the right voltages where they have to be, current would follow and obey the laws. You don't have to worry about that. Okay, so if a device is rated, let's say 5 volts 1 amp, if I provide it with a 5 volt source, okay, a 5 volt source, and even if this 5 volt source can deliver 1,000 amps of current, this device is still going to pull just 1 amp. Only 1 amp of current is going to flow. Why? Because that means that the resistance of the device is enough to check how much current that will flow. Okay, so understand these things. So if it is an LED, okay, if it is an LED, if the voltage matches, you actually don't need an external. So if it is, let's say, red and I have 2 volts here and I have 2 volts as my source, I actually don't need an external resistor. You can try it. If you have kits, you can try it. Just if you have a bench power supply, set it to 2 volts and connect a red LED and see. If your bench power supply is not faulty and its readings are accurate, the LED should do fine. Okay. However, the problem with LEDs is that the manufacturers actually don't get the variations very well. Is that okay? You can actually buy the same set of LEDs from a manufacturer and they will have the same different brightness. Okay. Now, even with LEDs, because LEDs are diodes, this is what I've witnessed. This is what happens when you connect them in series. Okay. So I can still put a resistor here on the LED. Okay, so let's say I have 2 volts. You can try this out. Now, what will happen is that if the LED were to be a linear device, like a light bulb, a DC light bulb or something, which is a linear device. So let me draw that one also here. 2 volts. I have a resistor and I have a linear incandescent light bulb over here, right? For this situation, because both of these guys are resistive, the voltage drop across here would divide, will undergo division. Okay, the voltage drop across this point will undergo division. But if you observe for an LED, you realize that the voltage drop across the LED would always be high. Will always be higher. In fact, when I did the experiment, as I kept increasing the voltage, initially the voltage was only increasing across the LED until the LED opened. Remember, it is a valve, right? Until it opened enough for current to flow. So as the current began flowing, Ohm's law says that the voltage drop is a reaction, it's a product of the current flowing and the resistance. So until this LED actually opens up, and the LED will only open when it gets the right, it overcomes its forward voltage drop. Okay, so until the LED overcomes its forward voltage drop, current is not going to flow. And so when you check this, you realize that if there is any voltage buildup, it will be building across the LED, not across this. So after this LED has opened up and is now conducting, any excess voltage now begins to speedily increase across the resistor instead. Okay, so that is the reason we call these things protective resistors. Now, if you want to confirm what I'm talking about, if you know how to use any simulator, you can try it. Okay, just put a voltmeter across an LED and a voltmeter across a resistor, like in this series, right? And then vary your voltage and look at check how the voltages split across there. Now you do the same for a lamp and then a resistor. Now you realize that because these are resistive elements, right from the word go, they begin dividing the voltage among them according to their resistance. Okay, so please understand these things when you talk about them. Okay, if the voltage matches, I don't need resistor. So one way you could think about this is that the reason you need a resistor is to cater for excess voltage. Think about it that way. If you have any circuit, right, that you are supposed to power with a battery, the reason you need a resistor is to cater for excess voltage. So let's say if my volts here is 5 and I want to connect, let's say, a green LED, for instance, okay? A green LED, let me admit this one. A green LED would usually work from 2.8 volts to about 3.2 volts. Okay, so let's say we target at 3 volts. That means that I have to deal with this extra 2 volts here. That means I will need a resistor to drop this extra 2 volts. Is that okay? So the next thing I have to think about is how much current do I want to power the LED with? So let's say if I choose 10 milliamps, then it means that this resistor also has to allow 10 milliamps of current, to flow through it. Is that okay? So think about it this way. Anytime you need a resistor in such a configuration, you only need the resistor to deal with the excess voltage always think about it that way. So if you don't have any excess voltage, then you don't need any excess any resistor to deal with it. Okay, good. But like I said, for LEDs, you can actually put this there and it will still turn on, just that it will affect the brightness a little bit. Okay, but you don't always need resistors so far as voltage is matching. Please, any questions before we continue? Yes, and somebody also asked, is it advisable to use LED resistors as voltage regulators? Let me just try and go talk about that briefly. Okay, where is my mouse? Okay, so let me first get rid of this. Okay, so the answer to that question, in fact, I'll go for a strong no because you said voltage regulation, so I'll say no. Why? Yes, I can divide a voltage with resistors. Okay, we know that. So if let's say I have, sorry, if let's say I have 12 volts over here, and then I want, let's say, 9 volts out of it, right? I could actually do a series arrangement like this, and then tap voltage from here. So the idea is that I need 9 volts from here. Is that okay? All right, this is possible. Okay, so let us work out the values of the resistors. If we want 9 volts here, we can do a lot of resistor configurations that will give us 9 volts over here. Okay, now since we have 9 over 12, that will give us, so 3 will go here 3 times and go here 4 times. Okay, so we need to select 2 resistors such that I think we should have this ratio. Let's call this R2, let's call this R1, so that the ratio of R2 to the total resistance is 3:4. Okay, we can select so many different resistor values to achieve this. But you see, what actually matters is how much current are you going to draw from this junction, from this divider. Okay, because we are using resistors, the moment, let's say in the beginning we create, and we know we can steadily say that okay, the current requirement is going to be 100 milliamps, right? Yes, we can use this. So I could say that okay, if I need 100 milliamps through here, then I'm going to choose this resistor so that it can pass, let's say, 101 milliamps. Okay, so I'll let 1 milliamp draw a drive to ground to stabilize this, and I'm going to draw the 100 milliamps through here. Okay, so we can use this calculation to actually choose values. If we want, we can do it. Okay, let's do it probably. So if I want to do this, so that means this R1 here has to drop 3 volts. Okay, so V equals to IR. So we need to know the value of the resistance. Now, if we make R the subject, we get V over what? Over I. Is that okay? So we need it to drop a voltage of 3 volts, and we need it to pass. Since the current is coming from here, all the current has to pass through. So at a current of 101 milliamps. Okay, somebody should quickly compute this for me. 3 divided by 101. Now, there is a textbook way of doing this. Okay, there is a textbook way of doing this, but I like to do it intuitively. That's why I'm showing you that way. Yeah, a question. What did you get?
0.0297.
So convert 0.0297. So it's a milli. So if you convert it to a normal value, what would that be? 0. So okay, it said 0.0297, right? Right?
Yes.
Okay, so that means 29. That's about 29 ohms. True of us. So if we divide by 1,000.
Divided by 1,000.
Because this is
Becoming
milli. This is milli. So milli will go up and become a K. Okay, so that means, sorry, that means you have to multiply by 1,000, not divide by 1,000. So if we multiply 1, 2, 3, so that will give us 29 ohms. Okay, so it means that we have to choose an R1 of 29 ohms. And again, we have to also consider the power rating of the resistor. But for now, let's ignore that. Now, you see, when this current gets here, I only want 1 milliamps to go through this and the rest to go to power whatever we have connected it. Okay. So the trick here is I just have to consider this 1 milliamp and the voltage I needed to drop. So R2 can be calculated as 9 volts, which is the voltage we want across it, and then the current that we want to flow, which will be 1 milliamp, and this should be something I think 9 kilo ohm. Now, intuitively, if you understand Kirchhoff's law, you know that this is going to happen. Okay, so if I create this circuit, this is going to allow 100 milliamps to go through. And you see, so far as I am pulling exactly 100 milliamps, everything will be okay. But the moment I pull less or more, then this voltage is going to change. Okay, but when we are doing voltage regulation, for instance, when we use an IC like LM7805, it promises a constant 5-volt output irrespective of whatever we are drawing. I mean, so far as we are drawing current within the range it offers, okay, and we are supplying voltage within the range that it offers. But you realize that this is not robust for when you use potential divider. Again, when assuming this is battery powered, as we are using the system's voltage is going to change, and any change here is again going to change our output. Okay, so if you want a very reliable voltage regulation, please don't use this. But of course, if you are just using it for maybe splitting, sensing, and those kind of stuff, then you can use it as a potential divider. I don't know if that answers the one who asked this question. Please, any questions on this? We have just a few minutes to end this session. Any questions on this? And let me also clarify again. There is something called the Thevenin theorem, okay? In the textbooks, that's how you would actually deal with this. But this is also an intuitive way to go about this, and it works. If you use the Thevenin theorem for this, you are going to get the same result, okay? Just that the Thevenin theorem is a more formalized way of doing these things. Okay, please, any questions? Or I have confused you. Any questions? Any questions? Let's talk about this. Do you have any questions? Any questions? Okay, I'll take that as no questions and let's proceed. Okay, so when you learn these things, please don't just learn them for learning's sake. Okay, try to understand where the reason we talk about them and all those kind of stuff. Try to get the whole thing. Okay, huh. And it was good. People were able to, I mean, explain in their own words and in their own way what they think that the Ohm's law is about. In fact, I think I liked it. I liked it. So keep that up, okay? Keep that up. Always try get more understanding, okay? Don't just take the textbook for what it is. Try understanding it. There is always a deeper understanding if you search for it, and you can always get it, okay? All right, please, any more questions? Any questions? Continue. So let's quickly finish up our PowerPoint. Let's quickly finish up our PowerPoint. Please, those can you see my, okay, let me stop sharing and share again. Okay, so welcome back. Welcome back. I believe things are clearer. Please, if you are still having some confusion, let me know, okay, so that I explain to you. But understanding this thing is very important. It makes the whole circuit design process simpler because, okay, so take note. When you are dealing with circuits, just concentrate most of the time, just concentrate on getting the right level of voltages to where they have to be. Okay, current will always follow. Don't worry about current won't rush itself. Current will only obey the command of voltage and react accordingly based on the resistance of whatever material it is flowing through. Okay, so take note of that. If my voltage matches my requirements, there is no need for a resistor. Always think of resistors as using it to deal with the excess voltage, at least in this particular context. Okay, all right, so let's continue. So the mathematical statement of Ohm's law is this. Okay, so the voltage drop, and please take note that the voltage drop that we are talking about here has to be what is dropping across just that component. Okay, just that component. Okay, so if it is a resistor, just that resistor, no other resistor is included. Is that okay? So the voltage drop is always proportional to the current and the resistance of that material. Okay, now take note that this is a statement of linearity. I think, yes, it's a statement of linearity. And if you plot a graph for this, you're going to get a graph of voltage against current. You're going to get a straight line because it's a linear statement. And this does not apply to things like sorry, what do you call it? Diodes. Okay, diode is a nonlinear device. You can read more on it. I don't want to go into further theory stuff. Okay. So we can also express this as V equals to IR. So that is the mathematical statement for Ohm's law. Is that okay? Now, usually, if you are part of any electronic community, you would hear resistors being described in so many different ways. Okay, and usually the way you hear or the adjective that a resistor assumes depends on the way it has been used in a circuit. It usually depends on the way it has been used in a circuit. Just a moment, let me switch on the camera. Okay, depends on the way it has been used in a circuit. Okay, so let's look at some of the various ways we use resistors in a circuit. Okay, so let me just skip to this. So when you hear of a potential divider, this should be able to create a mental picture of two resistors in series. Is that okay? So as an engineer, if you hear something like, oh, a potential divider, you should immediately have resistors in series in your mind. Is that okay? Tapping and voltage from between them. Then if you also hear of something like a shunt resistor, sometimes you hear of, oh, putting a shunt resistor. When we use a shunt resistor is basically a resistor that has a very low resistance. Usually we use them for current sensing. Okay, so when you hear of that, if you tell any electronics engineer shunt resistor, it immediately gives them a clue about what that is. Okay, then sometimes you hear of pull-up resistor. Usually when you are dealing with microcontrollers, pull-up resistor. A pull-up resistor is just a resistor that has been tied to a signal line that is connecting a signal line to a higher voltage source, usually 5 volts or 3 volts, okay, depending on the technology. Okay, so something like this is what we call a pull-up resistor. So if you ever call me and be like, oh, prof, I placed a pull-up resistor on pin 5, immediately I will understand what that means. Okay, then when we use the resistor to connect the signal to the ground or the pin to the ground, we call it a pull down resistor. And usually you also hear of current limiting or protective resistors. That is usually used in things like when you want to connect an LED to a power source and all that. Okay, so these are various ways that you could hear people talk about resistors in special cases. Okay, all right. Now the next thing I want us to look at is the fact that resistors. Yesterday when we talked about capacitor, we realized that capacitors could have a fixed value or a variable value, right? Now the same thing applies to resistors. Resistors could actually have a fixed value. So for instance, there could be a resistor that is rated 10K, 100K, 1 meg, and so on. And this value in normal circumstances, let me put it that way, would remain the same. It won't change. Is that okay? Now, emphasis on normal circumstances because resistance is actually affected by temperature too. Okay, but we won't go there right now. But in normal circumstances, if a resistor is rated, let's say 10K, it has to remain what 10K. Is that okay? However, resistances can also be variable. Is that okay? They can be variable, and usually we use these variable resistors in operations where we would want to interact with our circuit during when it's being used. Is that okay? Now, in terms of how we can vary the resistances, there are so many ways. We can do it by mechanical means. We can do it. We can vary the resistance by electrical means. Now, take note. If a variable resistor can be adjusted by mechanical means, that means it has been designed to be adjusted by mechanical means. If it is adjustable by mechanical means, you cannot adjust it by electrical means. Take note of that, okay? So there are also digital potentiometers. Sorry, we can vary them by electrical means. We can vary some by changes in temperature. Some can be varied by changes in light intensity, okay? Now, there is a special one called, there are some special resistors I'm going to talk briefly about. Then the first one is an LDR, what we call the light dependent resistor, okay? Now, this is a type of resistor whose resistance can be varied by changing the light intensity. Okay, so usually we see them in photosensing applications. Okay, so in case you haven't seen one before, that is it. So I can use for instance, if I have an outside light, we need outside light work during the night. Is that okay? So assuming I am a night worker usually I don't close early, so maybe even as at 8 p.m. I'm not in my house. That means that I can do two things: wait till I come to the house before I turn on my light, or once I'm leaving the house in the morning, I could switch on my light and it will remain on till the night, right? But I realize that if you do that, one, you are incurring more costs and you are not doing your country any good, right? So it's not something you should do. So one way you could solve this is by using an LDR, creating a circuit with LDR to detect the day and night, and you can use it to switch on or off your lights appropriately. Okay, so that's one of the applications of an LDR. There is also a type of resistor called a thermistor, whose resistance vary with temperature. Okay, so when you change the temperature of their environment, their resistance also what changes. Okay, so the word thermistor is actually derived from thermal and resistor, so it's a combination of that. These are examples of thermistors, so they are usually seen in heat sensing applications. Okay, so definitely your rice cooker should have something like that, or yes, your rice cooker should have something like that. I don't know if rice cookers actually use thermistors or they use like ordinary thermostat or something like that. Okay, but if you have any heat sensing applications, chances are that you can use one of these thermistors to handle it. Okay, so there are special types of resistors. Then we also have what we call the potentiometers. Now these are devices that are by default created to serve as voltage dividers. That's what we call potentiometers. But voltage dividers are also called potential dividers. Okay. Now, these potentiometers by default or generally would have at least three terminals. Okay. Now, what we do with them is okay. So these are examples of them. Okay. So we have several potentiometers, sliders. Okay. Any of them, so they are all potentiometers. Okay. They are used to create voltage divide. They divide voltage. Okay. Now, internally, this is how they look like. So, if you take something like this one, there is this area of resistive material, and we have connector 1 and 2 connected at the ends of this resistive material. Now, remember in the beginning, I said that if I take any material, let's say copper, and I take two pieces of copper wire, same cross sectional area, but I vary, let's say, the length, that is going to lead to differences in resistance. Okay, so this is engineered such that this resistance, the full if I move from here to here, I would get a specific resistance, okay? And there is a middle pin which is connected to something we call the wiper that can actually slide over this material. So if, let's say, I'm measuring between this point and that point, then as I vary the wiper over this resisting material, I would in effect be varying the resistance, the total resistance of of the the device. Is that okay? So that also means that if I connect this to this pin 1 to 5 volts and pin 2 to ground, then depending on the position of the wiper, I have what we call a potential divider or a voltage divider. Is that okay? Good. But then you could actually configure this in another way to form a variable resistor. So take note, by default, they are potential dividers. That's why we call them potentiometers, okay? But I could configure them in some way to serve as a variable resistor or a rheostat, okay? So another name for variable resistor is a rheostat. Okay, so look at this configuration. If I connect 5 volts here to pin 1, 5 volt to pin 3, and the middle to as an output to anything. This is a potential divider configuration. Is that okay? But if I connect only 2 pins, pin 1 and the wiper, so if the wiper and any other pin, then I have connected it as a variable resistor. In this case, it's going to function as a variable resistor. Is that okay? So take note of that. It's going to function as a variable resistor. So these are the two ways you could configure a manual potentiometer as a variable resistor. Okay, so let's continue. Now, we can actually also describe resistors in terms of the material that they are designed from, okay? So we can have a category of resistors called the carbon film resistors. We have the metal film. Yeah, Joel, you can ask your question.
Please, I'm quite confused about the variable and the potentiometer.
Okay, so let me take, you mean this, right?
Yeah, you were explaining the potentiometer and the variable, and I'm saying that I'm somewhat confused. I didn't
Okay,
get it
so
right.
potentiometer, okay, is a different configuration that this particular thing we call port can be used. Now, take note, when we are talking about potentiometer, here we are interested in voltage division, okay? We are interested in voltage division, not what do we call it? Resistance variation. Now, remember when we looked at both potential dividers or voltage dividers, we said that the division of the voltage is as a result of the differences, the ratio of the resistances of the resistors used, right? And this material actually contains a resisting material. And as we are sliding over, we are in effect just varying the voltages, the voltage division, okay, the ratios of the bottom side and the upper side. Is that okay? So that results in different voltage. So let's say I connect 5 volts and ground here. That means that I can select from ground up to 5 volts. Okay, while by varying this particular point, I could select from ground up to 5 volts. Okay, but then again, there is something wrong when you just do this, because if you hook this up directly to ground, okay, if you connect this wiper such that is directly connected to ground, then I think there is a possibility of short circuit. Okay, but I won't go into that right now. So if we do this configuration, here, we are actually selecting the output here is going to be voltage selection. We are not doing, yes, inherently we are doing resistance variation, but the main purpose of this configuration is for voltage selection. So I can adjust my voltage output on this between ground and 5 volts. Is it okay?
Yes, sir.
Okay, but then when we configure it like this, then it becomes a variable resistor. So take note that there is a difference between a variable resistor or a rheostat and a potentiometer. These are two different things. But over here, what I'm trying to tell you is that the same device, which we call the port, can be configured depending on how we use it. It can serve as its default potentiometer, or we could configure it and use it as a variable resistor. Okay, so they are two different things.
Okay, thank you, sir.
Okay. All right. Thank you. Thank you. All right. So I was talking about this. So depending on the material that we use to create that particular resistor, okay, we could classify resistors as carbon film resistors. That means they are made from a carbon film material. Metal film resistors. We could also have wire wound resistors. We could have metal oxide resistors, metal strip, and all that. So all these just is because of the material they are created from. Is that okay? So yeah, if that is what you want to do, Kim. Now, since we are engineers, one of the important things we need to know is what to consider when we are choosing resistors. Okay, this is very important. The things that we have to consider. Yesterday we looked at that for capacitors, what to consider when you are choosing capacitors, what to consider when you are choosing diodes. Right. Today we are going to look at what to consider when you are choosing resistors. Okay, so basically, and I know probably most of you do this. Basically, for simple applications, you just have to worry yourself about the resistance. Okay, that's the value of the resistor. The tolerance. Now, the tolerance of a resistor is also the percentage error value error in the value, the stated value. Okay, and for resistors, you could get, I think I know of 1% tolerance. That means that resistor, if it is 1% tolerance, it only means that the value that you will measure if you use an ohmmeter would be very close, okay, to the stated value. You could also get 5%, you could get 10%, and you could get 20%. Okay, these are the tolerances that I know. Okay, so you basically need to worry about the resistance, the tolerance, and the wattage. And for resistors, wattage is about the size of the resistor. Okay, the different. So we could have, let's say, a 1K resistor at different wattages. Okay, with the same 1K resistor, we can get it at, let's say, 1/8 watts. We can get it at half watt, quarter watt, 1 watt, 3 watt, in that order. Okay, so what will change is that a half watt 1K resistor will be bigger than a 1/8 watt 1K resistor. A 1 watt 1K resistor would be bigger than a half watt 1K resistor. Okay, so but in terms of wattage, that is it. And it is so because resistors primarily deals with the excess energy by dissipating them as heat. So the bigger the resistor, the more surface area it has to cool down quickly or dissipate the energy. Okay, that is why they come in different sizes. So different sizes, but we can get the same value for almost the various sizes. Okay, so these are usually the things, the parameters that you may consider when you are dealing with very simple applications. However, for some sensitive applications, okay, you may have to consider more than that. You may have to consider, especially when you are dealing with higher frequency applications or automotive applications where temperature is an issue, then you may choose resistors based on more parameters than just what you have stated. Now, in this case, you may have to consider things like what we call the temperature coefficient. Okay, now every resistor, let me say, every material has there is a way temperature influences the nature of materials. Okay, so let me just, in order not to go into details, let me just say that resistance actually varies with temperature. Okay, but there has to be a certain amount of temperature. Let me put it that way. So when I asked people to state about Ohm's law, somebody said at the same temperature or something. The person included temperature in his work, and that was very beautiful. Okay, so the temperature of the resistor actually does affect the resistor. Now, generally for resistors, when temperature is increasing, the resistance will decrease. That okay? So if I, let's say, have a 1K resistor and this rating is probably at room temperature. That's about 25 degrees Celsius, right? If I should use this temperature and its temperature, if I should use this resistor and its temperature rises to, let's say, 50 Celsius, there is going to be a decrease in the resistance. Is that okay? So that means that if the value of the resistor is supposed to be accurate, then changes in the temperature is going to cause your device to malfunction a bit. Is that okay? So depend if this is the situation, then you have to check that the resistor that you are choosing has a good temperature coefficient. Okay, so this is also one of the reasons why we have different materials being used for resistors. So we just saw that some resistors are wire wound, carbon film, metal film, and all that. All these material have different properties that make them ideal for certain situations. Okay. The next thing is the aging and stability. Of course, electronic components, as you are using them, they age and they begin to their properties or qualities begin to drop. Is that okay? So depending on your application, you may also have to consider the aging and stability of the resistor. And this is the point where you have to probably get in touch with your manufacturer or data sheet and read more about it. And manufacturers do good job. They usually have information about these things in their data sheets. Another thing is thermal resistance. Okay, thermal resistance. For instance, if you look at shunt resistors, you mostly see that they are the cement type, what we call the power resistors. Okay, so the material that you are using, you have to ensure that the material can withstand the heat or the energy the resistor is supposed to what dissipate. Okay, you can't just go about choosing any material. So if you look at the various types of resistors we have, if you take a shunt resistor for instance, because of its ability to dissipate a lot of energy, they use a special type of material to create it. Okay, I don't have one with me. I would have shown you, but you can check for power resistors online. You realize that they have different materials. Okay, and these are some of the things you have to consider. So the thermal resistance, okay, because it is dissipating the excess energy as heat, so it should be able to withstand that amount of heat. Okay, so in certain applications, you may have to consider these properties of resistors. Another thing that you may have to look at is its immunity to noise. Okay, noise. And this particular point comes in handy when you are dealing with higher gain amplifiers. Okay, because you usually bias your output and even your feedbacks, you use resistors for them. So if the type of resistor you are using, its chemistry is unable to withstand noise, the noise from the environment, and usually this could be minor thermal fluctuations. Okay, we saw that the temperature has effect on resistance. Okay, so if it is so sensitive to thermal fluctuations, then you may not want to consider such resistors for things like feedback operations and amplifier gain operations. Okay, and then finally, high frequency behavior. Okay, whenever you are operating in the gigahertz region or very high frequency region, then the innate inductance of the material used for the resistance becomes an issue. Now, this is not a concept I would want to talk about in here. Probably I would have a session to talk about this kind of high frequency behavior of certain materials. Okay, when we get to certain frequencies, which we usually classify as high frequency in electronics, like in the gigahertz, trust me, the things you call capacitors, inductors, and resistors, they tend to behave differently. Okay, now that's a topic for another session. Now, I think that would be. Oh, okay. I think I still have more. Still have more. Oh, yeah. It was just a duplicated PowerPoint. All right. So that is the end of what I wanted to talk about. So we still have some time to kill. I would use it to answer questions if there are any, as we bring as we bring this point to uh, as we bring this session to an end. Yeah. So, any questions? Any questions? Any questions? Any suggestions from the senior members? Yeah. Please let's discuss. Any questions? Any questions, please? Yeah. Nikat, yes. Nikat, you can go ahead.
Yes. Why we are using pull up register and pull down register?
Uh, Come again. I didn't hear you well.
Why we are use pull up register and pull down register?
Oh, okay. So he's asking that why do we use pull up or when do we use pull up resistors and pull down resistors? Okay, so let me probably go. I think yeah. Let me use the project we are doing as an example. There is an example in there. Okay, so I'm quickly going to share the key card view. Okay, right. Okay, good. Please, can you all see the key card view?
Yes, I can see.
Okay, fantastic. All right, so Nikat, look at this. For instance, the reset pin of the Atmega 328 microcontroller, okay, it has to be by default high. I mean, by default, it has to be connected to 5 volts. Do you get it? Do you
Yes,
get it?
yes,
Good.
yes,
So, for instance, if look at something, when I want to, if I want to reset the microcontroller, then what I can do is press on this button, right? So
yes.
let me just delete this and connect this there. Okay. So if I do this, this will work. Okay, it will be connected to 5 volt. That's good. But when I want to reset this, I will have to press on this button. Okay, when I press on this button, since this is ground, it is going to link this point to ground. Okay, that is what
Mm-hmm.
instruct the microcontroller to reset. But the problem is that when I press this button, I have actually short circuited the device. Do you realize that?
Yes.
Exactly. So in order to avoid the short circuit, I will put this here. And so if I press this whilst I have this resistor here, it limits how much current is going to flow and I still achieve. Oh, okay. Somebody said, oh, sorry. So the I thought I was sharing the schematic, not knowing I wasn't. Sorry. So probably let me take it again. Thank you very much for drawing my attention. I hope. Okay. So this is what I'm saying. You see over here, this RST pin, right? Pin one
Mm-hmm.
is supposed to by default have a higher voltage. Is that okay? Which is it's supposed to be connected to 5 volts in order to work. Because the moment it goes low, in fact, if you try to start this at mega and this pin is low, it will never turn on. Okay, it will never turn on. You can try it. Okay, so in order to ensure that that doesn't happen, by default, we should connect this point to 5 volts like that. Is that okay? So that when we want to reset it, it's an active low signal. So when we reset it means we have to put a low signal on the pin. And we can do that by pushing this reset button down. When we push it down, since this is ground, it will link this line to the pin to ground and it will reset, right? But the problem is that the moment we do that, we have also short circuited our 5 volts line, right? Which is not a good thing. So to solve that, we will put in this 10K so that when we press on this and this guy joins the ground, the current that will flow to the ground will be limited by this resistor. Okay, so the pull-up resistor is supposed to ensure that this signal will by default be connected to what 5 volts. Okay, and you see the thing is, because there is no this RST pin is not actually sinking current. Current is not flowing into it technically, right? The only way current will flow would be if we press on this resistor and it connects to ground. So far as we have not pressed this pin, the voltage here will be the same as the voltage here, because remember Ohm's law says that the potential difference across is proportional to the current. So if there is no current, right, then we are not going, the voltage that will be across here, in fact the voltage that we measure at this point will be the same as the voltage that we are putting at the source. Okay, but in the moment we press on this, then current is going to flow and we are now going to have the 5 volt drop across this. So without pressing, if you try to measure voltage across this, you get 0, because this is going to be 5 volts, this point is also going to be 5 volts. You can try it out. Okay, so that's the function of the pull up resistor. Now it becomes a pull down resistor if instead of connecting it to the 5 volt, we connect it to ground. So in that case, we will do that when we rather want the pin to be a default low, not high. Is that okay? So that is when we use the pull up and pull down resistor. So it has become a common thing in the field, such that anytime you talk about pull up resistor or pull down resistor, any electrical circuit designer actually understands what it is. I don't know if I have answered your question.
Yes.
Thank you.
Very much.
Yeah, please, any other questions? We have just 9 minutes to end this session. Any more questions, please? Any more questions? Any more questions? Any more questions? Yeah, David, yeah, please, you can go ahead. David, I thought you wanted to ask a question. Okay.
Yes, I'm asking already. Okay, I'm muted already. Sorry for that. My question is, why designing a device for both temperate and like snowing region? The other time we talk about changes in the resistance based on the temperature like that. So is there any means whereby we can design a device in choosing resistor that will work for both temperate region and a snowing region? So that's my question.
Okay. So thank you. You are asking that, is there any way you can design a device for any weather condition, right?
Exactly, sir. Yeah.
Exactly. Okay, so you see, for resistors, you don't even have to worry about I don't know even if you have to worry about the cold regions, right? The problem would be with the hot regions. Is that okay? So I think for resistors, then you just have to worry about in the hot regions. Probably you could isolate your circuit from the environment, right, by heat sinking and all those kind of stuff. Or if it is the resistor itself that is generating the heat, then you should probably heat sink it. Applying heat sink and also choosing the right type of resistor would help it cool down faster. Is that okay? And of course, sometimes too, you can employ some cooling mechanism. Is that okay? So yeah, you could actually do that. Please, are you
Alright.
okay?
Thank you.
Yeah.
Yeah, I'm okay with that. Yeah.
Thank you. Yeah. So please, any other questions? Any other
Yes.
questions?
Can you please share the schematic diagram?
Are you on the WhatsApp page? Are you on the WhatsApp page? I shared it there this morning.
Yeah. Yes,
Yes. So
I'm on
I
the
shared
WhatsApp
an
page.
image of it. However, for the actual files, I'll share them after the project. I want people to actually design things for themselves. So I'll make the files available on our GitHub page, but for now, I will only be sharing the images. Okay, so that in case you want to follow, you can look on it and build for yourself too. Yeah.
All right.
All right. Thank you. Yeah, maybe one more question, then we are out of here. We're prepared for the second session. Okay, so in the second session, we are going to continue with our board. We're going to assign footprints, and then do probably, I think we also start with the component arrangement, but I'll initially talk about the component packages, the package types. Okay, I'll talk about the package types before we start that. Okay, so if there is no more question, then I'll say thank you for joining this session. I'm still inviting you to the next session. Don't miss it, and let's meet in the next 1 hour 30 minutes. Okay, thank you very much.